Hi, we are now going to learn about electronic devices. And the easiest part about electronic devices is digital electronics. Actually, it's not just that it is easy, everything around us today is digital electronics. Okay? So for example, wall clocks like this were common earlier. Now we are moving more and more to digital clocks. TVs like this, they are also electronic TVs, right? Clearly. But these are the old type of TVs. And today, all the TVs that we get are LED screens or LCD screens, and these are all digital TVs. Similarly, the old telephone is being replaced by the new telephones. I mean, you don't even see this anymore. And not just these, everything around us, when we talk about computers, calculators, even you take cameras today. In fact, even this is getting out of fashion now, right? Because everybody is now only using their mobile. Now, the world all around us, whenever you look at an electronic item, you're talking about digital electronics. But why did the world move to digital? To understand this, we have to think about what is the difference between the older kind of electronics, which is called analog electronics, and the new electronics, which is the digital electronics. Why did the world become digital? To understand why the world has moved to digital, we have to understand what are the problems with the earlier system, and the earlier system was called analog. In an analog system, the signals that are sent are continuous. In a digital system, the signals are discrete. So what is the problem if you send a continuous signal? Let us try and understand that. For example, suppose a TV station is sending a signal, your TV has to receive it, right? So you have a source and you have a receiver. But you don't get a signal straight from the source to a receiver. You have a bunch of intermediate stations which will receive it, amplify it, and then pass on to the next one, right? Maybe it is going from the TV station to an antenna, and from the antenna it may go to the satellite, and then it may come back down to another antenna, and then you may finally receive it, right? So from the source it goes in here. This is going to amplify it and send it here. Now when I'm drawing it like this, you must remember this may be thousands of kilometers long, hundreds of kilometers long, right? So from here, this system is going to amplify this, pass it on, and so on. And finally, the receiver receives it. So what kind of problem will come up? Whatever the source is sending, won't the receiver receive it? Anyway, all these things are just taking the signal and amplifying it. Let us look at it. Okay, so let us say that the source is sending something like this. It is a continuous input, right? When it is sent here, you can see that there is a slight change. You may not even notice the change, but there's a small change, because in any transmission, there will be small changes that will happen. There will be noise, okay? And the signal also gets slightly distorted. Now, this system is going to take this and it's going to amplify it. But let's assume that this system was perfect. It is going to replicate it exactly. But this system does not know what was originally sent. It is only taking what was received. Now, when it is sending what was received, but this channel, let's say, was about a couple of 100 kilometers. By the time it comes here, you're going to have a distorted signal, right? You can see that there is a small distortion that has happened, right? Well, it looks like this. It looks broadly like this, but there is a slight amount of distortion. Now, this is going to take it and it's going to amplify exactly. Let's assume this was perfect. So it's not adding any noise. But then whatever is sent, when it goes through this channel, again, there is some more distortion. Notice, on top of this distortion that happened, there is one more level of distortion that has happened. Okay? Now, this starts to look very different from that. Now, when it passes through this system, let's assume is perfect. So, no distortion here. But the channels you can't control. So, when it is going to be sent through this channel, right, it is transmitted from here to here, then there is a lot of distortion. And ultimately, this is what is received here, and that is what can be passed on to the receiver. So what did the receiver get? This signal. What did the source send? That signal. Okay, are they the same? Let's compare. Do they look the same? No, right? Huge amount of distortion has happened. At every stage, it was a small amount of distortion, right? You can see small distortions. But all of these errors are accumulating, and there is no way for each of these systems to correct those errors. You might wonder, but won't digital systems also have the same problem? Won't they also keep having these kinds of distortions? Of course they will. But there is a huge advantage when you're using a digital system. The errors get corrected, they don't accumulate. How does that happen? Let us now look at digital systems. When we are trying to use a digital signal, again from the source to the receiver, it is not going to be sent directly. There are going to be multiple intermediate points that will receive the signal and then amplify it and then send it to the next stage, right? So how is it that in digital systems, the errors get corrected at each stage? Let us look at this carefully. The source is going to send a signal like this. Notice there are only two values. This value, which I'll call as 0 volts, and that value, which I'm going to call as 5 volts. That's all. It is 0 volts, 5 volts, 0 volts, 5 volts, and so on, right? That's all you have. You don't have anything which is neither 0 nor 5. Now, all these systems know that there are only two values allowed, 0 or 5. Now, when the source sends this signal to that, right, through this channel, there is going to be distortion, small amount of distortion. Now, it is a small amount of distortion, but that means the 5 could have become 4.7. This 0 could have become 1.2. But this system knows that 1.2 is not allowed, 4.7 is not allowed. It knows that 1.2 probably was just 0. 4.7 was actually 5. So what this system does is it takes this and it says, okay, if it is 4.7, put it back at 5. If it is 1.2, put it back at 0. So this system corrects it. And what you get is back to 0 and 5. That's it. And now when this system is amplifying that and transmitting, by the time it comes here, definitely in this channel which you have no control over, there will be distortions. But these distortions are not so big that something that was at 5 has become negative or has become 0. No, it has become small up and down there. Similarly, 0 has gone up and down here. And this system knows that you only have 0s and 5s. So that means it will take this and say, okay, this is close to 5. So it basically corrects it and makes this 5, corrects this and makes this 0. So the output of this intermediate stage is back to where we started, 0s and 5s. And when that is sent here, again there are errors. It is not as if there are no errors. There are errors. When you're transmitting, there are distortions. But at each stage, the distortion is getting corrected. Okay, so this distorted signal, this system is going to correct it. And it's very easy for the system to correct. If it is close to 5, that means it is 5. If it is close to 0, that means it is 0. Right? So it just simply corrects it and sends this signal to the next stage. At each stage, what is being received is a distorted signal, but what is being sent is a corrected signal. So this is what the receiver gets. And now, is this the same as what we had sent? Let's compare. Look at that. It is exactly what we had sent. So at each stage, there are errors. It's not like there are no errors. This is definitely, you can see, there are errors. You can see errors. But at each stage, the errors get corrected. So the errors don't accumulate. In digital systems, the errors don't accumulate. Okay, so that means you can receive what was exactly sent at the receiver. This makes a huge difference because that way errors don't accumulate. You will see that digital systems, this is the single most important point about using digital systems. And if you can replicate what was sent perfectly, then there is no loss that happens. And that's why today the world has moved to digital systems. Our world has moved to digital because it's easier to transmit information without errors. But what exactly does digital mean? Digital simply means that it has discrete states. Instead of continuous states, it has discrete states. Often people confuse digital with binary because most digital systems that we use zeros and ones. But binary means there are two discrete states, 0, 1, true, false, on, off, all these are binary, two discrete states. Doesn't digital automatically mean binary? No. Digital can be binary, in most cases it is, but it's not necessary. Now let me ask you a very interesting question. When did our digital world start? When did humans first start using the idea of digital, discrete states? Well, you might think maybe 1960s, maybe 1970s, 50 years ago, 70 years ago. No, 5,000 years ago. Really? 5,000 years ago? There was no electronics then. But digital does not start with electronics. Our alphabet system, writing system is digital. It is not binary, it is digital. There are 26 letters, right? What do I mean by digital? You can write it like this, like that, like that. They're all different. But what do all these mean? They all simply mean A. Whether I write it like this or I write like this with a gap, you know that I'm talking about the same thing, A. Now drawing, suppose I were to draw, let us say one mountain here, I'm very bad at drawing, and let's say sun was coming out, okay, a childhood kind of drawing. Or if I draw a small hut here, now somebody copies this, there will be small changes, small errors, because this is continuous. And when they copy and then copy and copy, we make many copies of it, and somebody uses that to make one more copy and so on, you will see that the final drawing is different, because this is not discrete. This is a continuous drawing, right? You can make small changes to it, and the small changes can accumulate. This is analog. Whereas the alphabet system is discrete. Suppose I write it like this, the next person will write it back like that. Suppose I write it like this, you know that this is equal to that. They all look different, right? This looks a little bit different from that, but you know that they all represent A. So the alphabet system is digital, and that revolutionized the way records are kept, right? Writing is a digital idea. However you write with small changes, you know that you're talking about the same letter and therefore the same word. But of course, today we don't want to use 26 letters, right? We don't need 26 discrete levels to transmit 26 letters. It turns out that if you just use 2 discrete levels, you can represent everything that you need. Okay, just 2 discrete states can be used to transmit any amount of information. So electronic systems today are binary and of course digital. Okay, but digital doesn't necessarily mean binary, but there is a huge advantage when you use binary systems because you have only 2 levels. So a lot of things get easier. So you can talk about true and false, 0 volts, 5 volts, 0, 1. And so most of the digital systems that we are going to be dealing with, they are also binary systems. But keep in mind that digital does not necessarily mean binary, though most of our electronics today with digital electronics is actually a binary digital electronic system. There are many situations where naturally there are only 2 discrete states. Yes, no, on, off, true, false. For all these cases, if we use 2 symbols, 1 and 0, that is enough to represent these states. We call these symbols 0 and 1 as binary digits. BI and the TS, they combine together to form bits. When we say we are transmitting bits, what are we saying? We are talking about ones and zeros. Okay? Now, I can use this to represent on and off. I can say that this is 1, this is 0. This is 1, that is 0. 1, 0. I can also use bits to transmit letters with 1 bit, right? 1 bit, which can be 0 or 1. How many letters can I transmit? Well, it can only talk about 2 states, right? So with 1 bit, we can transmit 2 letters. 0 can be A, 1 can be B. But I want to transmit 26 letters. This is not enough. Okay, maybe if I use 2 bits. The question is, how many letters can we transmit using 2 bits? What does that mean? The first bit, you can have 0 or 1. The second bit, you can have 0 or 1. So with 2 bits, you can have 0, 0, 0, 1, 1, 0, 1, 1. So there are 4 possibilities. So you can have 4 characters transmitted. This could be A, this can be B, that can be C, that can be D. So if I send 1, 1, that means I have sent D. If I have sent 0, 1, that means I have sent B. But I want to transmit 26 letters. This is not enough. Maybe if I use 3 bits, well, with 3 bits, how many possibilities will you get? You will get 8 possibilities. This first bit can be 0 or 1. The second one can be 0 or 1. The third one can be 0 or 1. So 2 into 2 into 2. So you have 8 possibilities. So 8 characters. Not enough. Maybe if I use 4 bits, well, you'll have 2 power 4, 16 possibilities. Again, not enough. What if I use 5 bits? 2 power 5 is 32, which is more than 26. So if I use 5 bits, then I have enough options available uniquely for each letter. So 26 letters can be transmitted using 5 bits. Okay, so that's all we need. No, actually you see, though 26 capital letters, just 5 bits is enough. We also want to transmit small letters. We also want to send 0, 1, 2, 3, 9, right? These digits. We also want to send some special characters like question mark, and etc. So we don't want to use only 5 bits. So the standard today is to use 8 bits. 8 bits is called a byte. Okay? This system of coding whatever you want to send in terms of these bits, 8 bits together, is called the extended ASCII code system. It encodes symbols, digits, letters, a lot of different things. For example, 0, 1, 0, 0, 0, 0, 0, 1. This set of 8 bits, right? It represents A. So there are 8 bits here. Similarly, we use another set of 8 bits, 0, 1, 1. You can see that it's almost the same, but there is a 1 here instead of that 0. This represents small a. Okay? 0, 1, 1, 1, 1, 1, 1 represents question mark. And 0, 1, 0, 0, 1, 1, 0, 1 represents the letter M, capital letter M. Okay, so using these codes, I can send a single letter or a single character, okay, like this. But usually I want to send words. For example, how do I send or write a word Amma, let's say, A-M-M-A, right? Well, it is one letter followed by the next, followed by the next, followed by the next. So this letter is this code. So if you want to send it, you will send something like this. This one, you can see, represents capital A. This one represents capital M. The next 8 bits represents again M. And the next 8 bits after that represents A. So this is A, M, M, A. Okay? And whatever you want to send now like this, in bunches of 8, 8. So each of these 8 is called a byte. So in bytes, we are able to then send whatever we want to send, because each byte then represents one of the characters. Okay. Now, of course, you can say, but you guys are being very English-centric, right? Everything is only about English, because you're talking about English capital letters, English small letters. What about Hindi? What about Tamil? What about different languages all over the world? Okay. So therefore, today we want to represent a lot more. So we don't use ASCII anymore. Slowly the world is moving towards Unicode. And Unicode, usually we have 32 bits representing characters. So 2 power 32 possibilities, which is huge. So pretty much whatever you want to represent, you can represent using Unicode. So the world is slowly moving. Still a lot of the systems use extended ASCII system, but we are slowly moving towards the Unicode system. Okay. Now you can not only transmit characters like this, you can also have images coded in binary. For example, if I want to send this image, you cut it up into small boxes, and wherever you don't have the black, basically white, you call it 0. Wherever you have a black, you call it 1. So all you have to transmit is 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, and then continue like that. Okay? So this basically is a binary way of coding images, which is of course used quite a lot. So you notice that using binary digits, we can represent images, videos, sound, okay, characters, pretty much everything that we want. And it is very easy to create binary electronic systems using 2 levels of potential, 0 volts and 5 volts. And therefore, that is the reason why our digital world runs on the binary system.